lecture 11, which is a fairly short lecture on some of the storage technologies. And I'll be talking about the mechanical ones, the ones that I know something about, which include pumped storage, hydro, flywheels, and compressed air energy storage. This is the graph from the Sandia report on storage that I showed you yesterday. On the vertical axis is discharge time, horizontal axis is power rating. So where you sit on this curve, on this graph, says how much power you have to provide to the grid and how long you can do it for. And I pointed out that the heavy lifters in this, as we say in English, the technologies that can provide a lot of power for a lot of time are basically pumped storage, hydro, and compressed air energy storage. The other very common technology that you hear a lot nowadays are lithium-ion batteries, which are falling rapidly in price at the moment. There's quite a lot of them going into electricity grids like Australia, where I told you the issues with distributed renewable energy are particularly severe. We had a look at that yesterday. There's a whole range of battery technologies and fuel cell technologies that take the middle ground on this curve. And down the bottom, we have flywheels and supercapacitors, both high power and high energy supercapacitors. I am not a chemist, and I am not a physicist, so I cannot really tell you anything seriously about oops, I was just getting my laser pointer out, about batteries or about supercapacitors. The other thing that I pointed out yesterday was the top end of this graph is measured in hours. So the conventional energy storage technologies that we have are usually limited to times that are less than a day. And if you have the need for, say, seasonal storage, then that is a particular challenge at the moment, how to get seasonal storage. And I gave you an example of a situation yesterday where one would want to do that. So the requirements that we consider for storage, obviously it has to be cheap. It has to have what we say in English, a high round-trip efficiency. And what that means is that the ratio of the energy or the power that is coming out of the storage has to be a good fraction of the energy going in. Typical best round-trip efficiencies that you see are somewhere about 80%. Okay, so pump storage hydro will have a round-trip efficiency of 80%. Compressed air energy storage tends to be a little bit lower. Lithium-ion batteries get close to 80%, as do some of those other technologies, and so do flywheels. We also want a fast response time, because one of the reasons that we have energy storage on an electricity grid, particularly with high penetration of renewable energy, is to be able to ramp up as the renewable energy production is falling. So we want a fast response time, and obviously how much power we can put out and for how long are other key aspects of it, which tell you a little bit about the niche or the place that these particular technologies satisfy or help to solve in the energy system. Okay, here's a pump storage hydro system. This is one that is in the US. Called Raccoon Mountain Pump Storage in Tennessee in southern US. It was first built about 100 years ago. just on 100 years ago. It has been upgraded in terms of a new pump turbine, but the basic system has been there for a long time. And the idea of pump storage hydro is very simple. You have an upper reservoir and you have a lower reservoir. And if you're going to store energy, then you do that by using the turbine as a pump to pump water from the lower to the higher reservoir. And of course, once it's at the higher reservoir, it's available then to discharge through the turbine, acting as a turbine to generate power. So maybe in terms of what's happening in California with the high ramp rates that are required around sunset, then some of the excess solar photovoltaic power could be used during the day to pump the water up into the upper reservoir, and then during the night, that upper reservoir is drained through the turbine to produce power at night. So it's an extremely simple idea. It's really just a development of the basic idea of hydropower anyway. Sometimes it can be difficult to implement because you need to have both an upper reservoir and a lower reservoir. And I've seen examples of pump storage schemes where at least one of the reservoir has been human-made. In other words, it's not a natural lake or some other reservoir. It's actually been artificially made to provide the water storage. So this is what a pump hydro turbine looks like. And these are interesting examples of turbines because they have to be pumps as well. So the easiest way to think about the difference is that when you have the available head in terms of the height difference that is going to drive your generator, your turbine is a turbine. So it is extracting energy from the flow to generate electricity. When you're pumping, the generator becomes a motor and you pump the water up the reservoir. And usually what happens with pump storage systems is that you use a combined pump and turbine. So the pump is both a pump and a turbine. Okay, none of them are very, very difficult because the things that give you an efficient design for a turbine are not necessarily the qualities that give you an efficient design as a pump. And so one of the downsides of pump storage schemes like this is that the efficiency of both the pump and the turbine are a little bit lower than what they would be if they were dedicated devices. On the other hand, if you had a separate pump to the turbine, that would be an expensive additional piece of equipment to the facility. So a lot of, particularly the modern pump storage schemes, have a combined pump hydro turbine. It's a relatively new technology and therefore there's not very much available on it. One of the few references that I could find on pump turbines is this journal article here, which at least gives you some idea of what the makeup of the turbine is. So we have the spiral casing, which is you can just see around the outside of the pump turbine here. And that spiral casing delivers the water when the turbine is acting as a turbine, very much like a Francis turbine. A Francis turbine has a spiral casing, or sometimes called a volute, that looks like this. And of course, as the water goes around the circumference of the turbine, some of that water is flowing into the turbine. The flow rate decreases as you go around, so the cross-sectional area of the casing decreases. A pump turbine has stay vanes and guide vanes, very much like what we saw for a Francis turbine. Where they're called wicket gates sometimes. Then we have the turbine on the pump runner, which is basically the blades, and below the blades is the draft tube. And the draft tube is a standard component of a Francis turbine, and it has much the same role for a pump turbine, except, of course, when the flow is going in the opposite direction, the draft tube is funneling or transferring the water into the runner, and then the spiral casing is collecting that water and taking it up to the upper reservoir. So the general features of a pump turbine look somewhat similar to those of a Francis turbine, but of course the detailed design would probably be very different depending on the flow rates and the heads that are available. As far as I know, these turbines are designed specifically for each individual application. So there's not a manufacturer doesn't have a range of models that they provide that you buy the most suitable one for your particular application. You would go to the manufacturer and they would design you one specifically for your application. Here is some information about the times that are required. So standstill to full load generation can be around about 2 minutes. Okay, that's impressive for a mechanical device. I suspect this requires this requires the pipework to be full of water. Okay, so if you also had to fill up the penstock and the other pipework first, this time would probably be a little bit longer. But 2 minutes is quite a reasonable time for a mechanical device. And for many applications with where you using storage to, say, back up renewable energy reductions in power, this sort of timescale is reasonable. It's not as fast as a battery, but it's still considerably faster than other types of generators like coal-fired and nuclear power stations, comparable to gas turbine generations that also have timescales about the same. Okay, we move on to yet another mechanical device, and this is a flywheel. And a flywheel is an extremely simple example. You simply have a flywheel which has the maximum possible inertia that you can give it and rotates at the maximum possible angular velocity. And the energy that is stored as rotational kinetic energy is obviously a half J omega squared, and that energy can be delivered to the flywheel by this generator and motor unit. I didn't point it out for the pump turbine, but the generator on top of the turbine here would also be the motor for the pump as well. Okay, it's very likely a permanent magnet generator, and it will work equally well as a generator or a motor. And the same thing happens here. This is very likely a permanent magnet generator, which doubles as a motor to put the flywheel up to speed. With the flywheel, there's two major problems with getting a high energy density out of a flywheel. One is the air resistance, and you can see down the bottom here a pump that pumps as much of the air out of this vacuum chamber as possible in order to minimize the air resistance of the flywheel. So it's a little bit like the windage losses that we saw for a Pelton turbine wheel much earlier in the course. Also, too, you want to rotate at very high RPM. And at high RPM, there can be problems with the material properties. The material can creep, it can deform in shape, and that can lead to problems like high levels of vibrations and things like that. So most flywheel systems have magnetic bearings to minimize those issues. And then from the generator or motor, there is the usual power electronics and then a grid connection. Okay, so this would be the usual rectification / inversion that we saw for wind turbines earlier. But of course, the maximum power point tracking algorithms and whatever would be very different in this case. Here's some information about a particular producer of flywheels in North America called Beacon Power. And you can see, for example, their biggest flywheel, 360 kilowatts, can discharge from 350 to 150 kilowatts in about 2 minutes. Okay, so very much the same sort of timescales that we saw earlier for the hydro turbines. Okay, in fact, for small amounts of power, they can obviously discharge much more rapidly than that. And one of the, not common, but one of the up-and-coming uses for flywheels in modern electricity system is to have them on the side of a wind farm. And you can use a flywheel to do short-term smoothing of the wind farm output. So the amount of power that's required can be quite small compared to, say, the rated capacity of the wind farm. But even then, if you have several flywheels on site, you can actually produce a much smoother output power from your wind farm than you would otherwise do. And there can be benefits in doing that. So there's a whole range of materials that are used for flywheels. The very basic materials like steel are very popular because they have a high density, and clearly a high density translates into a high rotational inertia when you rotate it. And then there's a whole bunch of other materials here, some of which are very fancy, but also, as I said, some of these materials are difficult to keep in one piece over a long period of time. So here's what a typical flywheel looks like. Again, I'm not advertising this to you. I don't have any connection with Beacon Power, the company that makes this flywheel. It's just that there's not a lot of them around. So to give you an idea of what this turbine can do, or what this flywheel system can do, I've given you the specifications here. And as far as I know, I'm talking about their flywheel that's rated at 360 kilowatts. So it's about 2 meters tall, about 1 meter in diameter. Being an American company, of course, they use feet and pounds. So 2,500 pounds will be about 1,000 kilograms, about 1 ton for the rotor. And you can see how fast they spin, 16,000 RPM. And of course, when you look at the formula for rotational kinetic energy, it's omega squared. So the highest possible value of omega that you can get is going to give you the maximum possible energy storage. And there's what it's supposed to be able to put through in terms of energy over its lifetime. As distinct from batteries, a flywheel can be fully discharged. Okay, if you go from the maximum capacity of the flywheel and discharge, there's no reason why you have to stop at this position here. You can keep going down till the flywheel is fully discharged. And that can be an advantage because other technologies like batteries cannot be fully discharged. Most batteries have to maintain a minimum level of charge below which you cannot go. I'm not sure that the fact that it's protected by 60 patents really means a lot to us, but you can see that as far as you can tell from this image supplied by the manufacturer here, it's pretty much the basic arrangement that I was talking about in this slide here. Okay, I move on to what in many ways is one of the most interesting technologies for energy storage. It's one of the most complicated because it's one of these technologies that is inherently not efficient But to increase the efficiency of it, you have to get more and more complicated in the mechanical design. And what I find really interesting about compressed air energy storage is that this technology was first developed to use with nuclear power. Okay, the first compressed air energy storage system was built in Germany in 1970. And at that time, Germany had a very strong program to build more and more nuclear power stations for electricity production. Now, the problem with a nuclear power station is exactly the opposite of the problem with wind farms and solar. Wind and solar ramps up and down very rapidly. Nuclear power cannot ramp up and down rapidly. And so the idea that the German developers of this technology came up with was, if you have an electricity grid that has a predictable cyclic variation in the load, then the ideal way to satisfy that is to have nuclear power stations that produce, whose output is the average load. So that when the load is less than the average, the nuclear power gets stored. And when the demand is greater than average, you use that stored power to satisfy that extra load. And so the nuclear power stations can just keep going along at a very even power output, which is what they like doing. And so the idea of compressed air energy storage was developed purely for that technology. So I find it fascinating that here's an example of storage that was developed for the reasons that are completely the reverse of the reasons why we're interested in storage for a system that is dominated by renewable energy. So the idea of compressed air energy storage is simply that the energy gets stored as compressed air. So when there is power available, the air is compressed. And the left-hand side of this diagram here shows you the process. So we have low pressure and high pressure compressors. They're driven by an electric motor, probably with a gearbox. And they go down to a storage system. And often that storage is an underground cavern. For example, in Alberta, we have a lot of salt caverns over most of the province. So Alberta actually is a very favourable place to have compressed air energy storage because it's relatively easy to form a large underground cavern to store the air. And you can see the air can go through both those compressors before it goes underground. One of the basic problems with the technology in terms of efficiency is that, as you know, if you compress air, you're going to increase its internal energy. Okay, and that obviously manifests as an increase in temperature. And when that air gets stored underground, that temperature is usually lost. Okay, there's an amount, I forget the actual percentage of typical values of this, but the temperature is often on the borderline between whether you would try and figure out how to recover it or whether you just let it go. If you let it go and don't worry about trying to recover it, you have a simple system, but you have a relatively inefficient system. And similarly for things like intercoolers, which are ways to also increase the efficiency of compression. There are extra complexity in the equipment, and while they increase the efficiency with which the whole system operates, they make it more complicated and make it more expensive. So the air ends up in a large underground cavern at high pressure. It can be stored above ground. and that compressed air can obviously be transported, it's probably not worthwhile to use it for those for that reason, because the energy density is not very high. And when you need to get energy from that air, you release it and run it through a high pressure and low pressure turbine, which drive an electric generator now. So again, we have a situation where a generator doubles as a motor. So it'll actually be a generator for the turbine side of it and the motor for the compression side of it. It's often common to augment or increase the power output of compressed air energy storage by actually combusting something like natural gas and adding that to the airstream to increase the power output. So, as I said, a fascinating technology in that it spans the range from electricity systems where the producers had no intermittency issues to electricity systems that have huge amounts of intermittency issues. And it's basically the same technology that you use for both. There's only 2 or 3 actual installations of compressed air energy storage in the world. And I think the main reasons for that is that trade-off between complexity and efficiency. It's hard to get a simple system that is efficient. And I think that so there's some research and development timelines on it. So I think the first compressed air energy storage system was the Humpdorf system in Germany in the late 1970s. And there have been some more since then, but certainly not a large amount of them. So that completes what I wanted to show you on energy storage. I still have one more thing that I want to show you because I think this is potentially really important for you people. Unfortunately, I've mentioned this before. So can you see? Let me go to the top of this. Okay, this is just a story that I pulled off the web about what's going to happen in the future for cleaner fuel, and it's a good title for the topic because it's talking about fuel and not just about electricity generation. My belief is that hydrogen is going to be an important component of a cleaner energy system in the future. And what this article is saying, and I found quite a number of articles saying very much the same thing, that Russia is poised to be a very big player in this market. So if that article is correct, that means that Russia has the potential to be a major supplier of sustainable hydrogen for the future. The way it works is that hydrogen can be produced from natural gas. The process that is used for that is called steam reforming, and it produces carbon dioxide. So if you're going to produce clean hydrogen from this process, that carbon dioxide has to be sequestered underground away from being delivered to the atmosphere. At the moment, that is a relatively expensive way to produce hydrogen. It would be much easier simply to produce the hydrogen and let the carbon dioxide just go up into the atmosphere. But I hope after 6 weeks of lectures, you'll be convinced that that's not a good solution to the world's problems. So capturing the carbon dioxide that comes off the reforming of the natural gas to produce hydrogen is seen as one of the best ways in which the production of the carbon dioxide can be localized sufficiently that capturing it and storing it underground, or even possibly using it for other chemical products or fertilizers or things like that, becomes viable. And the other interesting thing about hydrogen is that it is a way in which the boundaries between the different energy systems that we have in our society are going to break down. I could tell you in 6 weeks a lot of, I hope, useful information about the electricity system, the way in which we generate electricity and how we can do that in a more renewable way. But I was able to talk about that more or less in isolation from the other uses of energy that we have in our societies. Okay, what's going to happen with hydrogen is that there's going to be a mix of the different components of the energy system. So, for example, I was talking yesterday about some of the ways of dealing with intermittency with renewable energy, and I was talking about curtailment, where the wind power producers and the solar power producers actually shut down to avoid putting more electricity onto the grid. Now, imagine all the solar farms and all the wind farms are equipped with hydrolysis systems that produce hydrogen. Anytime that the electricity is not required for the grid, it can go in to produce hydrogen. That hydrogen can be stored and used for road vehicles, trucks and cars and buses and trains. And so the transportation sector of our economy becomes integrated to some extent, at least, with the electricity producing part of our economy. So I think what we're going to see with hydrogen, aside from the fact that there are huge opportunities for countries like Russia in the future in supplying hydrogen, it's going to make our energy systems much more interactive and work with each other. So, unfortunately, we don't have enough time to go into any of the real details with hydrogen. And in fact, it's probably somewhat difficult to do because at the moment, a lot of what people are talking about are actually good ideas that haven't yet been implemented fully. Carbon capture and storage has been around for a long time, but it's still a very problematic technology. All the pilot plants that have been produced around the world to trial capturing carbon and storing it underground have been having cost overruns and are not working to specifications. So it's not a trivial problem to solve, or it's not a trivial thing to solve all these problems. But if they can be tackled, I think we have, as a collective inhabitants of the planet, we have a much better future in store for us. So on that note, I'm going to stop. And I don't have any more material to present, so I can present you with a shortened session today, although I do see a question. Peter, you have a question. Do you want to unmute and ask it, or do you want to put it in the chat?
Oh, so I think that it will be much easier to ask you using the voice. So thank you for the lecture. Thank you for the overview about the mechanical energy storages. David, what do you think about the gravity energy storage using solid weights? Because, for example, Energy Vault project, I think you know about this project. It's really hype today, but I don't know why you don't talk about it in your lecture. So thank you.
Okay, that's a very good question. The answer that I don't talk about it is that I honestly don't know a lot about it. When I teach this course in Calgary, a large part of the assessment for the course is a project that the students do. And I tell the students, find some area in renewable energy that you're interested in and do a project on it. And last year, for the first time, one of the project groups did a project on gravity storage. And to be honest, that was the first time that I had come across it. I just, I read fairly broadly in terms of energy matters, but obviously not enough. I had not come across it, and I had not made the conceptual leap in my own mind that this was a good thing to pursue. So, Peter, what I would very much like to ask you is if you have some information that you could pass on to me about gravity energy storage. I would very much like to look at it, because some of the issues, for example, if you are storing energy in a large mass and you change its height to extract that energy, you've got aerodynamic problems.
Yeah.
You've got aerodynamic. I'm an aerodynamicist. So, I'm naturally very interested in it, right? But it's just one of those technologies that, what we say in English is that it fell below the radar.
I think that it depends on the size of the mass, because you can choke this mass and you can lift it one by one, for example, piece by piece. So, okay, thank you. It's interesting.
Yeah, so please, Ivan can pass on my email address to you. If you do have some information, I would really love to see it. I was going to read up some more on gravity energy storage since the last time I ran the course, but I just haven't got around to doing it. So yeah, it's my fault, and I apologize. And I really hope you're working on this to commercialize the technology.
So yes, we have one idea about it, and it may be a good idea. Yeah.
Okay. I wish you the best of luck. I hope it goes well. And if there's any point in there you need some aerodynamics help, I would be very pleased to see if I could help.
Okay. Great. Thank you.
You've got some wonderful aerodynamics people in Russia, but I would be interested. Yes.
Of course. Okay. So thank you.
Okay. Any other questions?
I have a question.
Yes.
Concerning wind and solar energy, what do you think about some problematic period of time of this intermittency? I mean, seconds or minutes. You say about flywheels, so it's just about a few seconds, maybe, right?
Mm-hmm.
So what's the main? So where is the big issues of intermittency?
Okay, I think the issues are going to be very much dependent on the situation. So take, for example, Denmark. I was talking about Denmark yesterday, and I was showing that there are times when Denmark produces a lot more wind power than it needs, but it's able to export it. But what happens when the countries around Denmark also have a large amount of wind power? There has to be a limit to which you can offload your unneeded energy to other people. On the other hand, that figure that I showed you in the lecture yesterday about the graph that had the various ways of dealing with intermittency, that was produced by a guy called Dick Perez, who does a lot of work on solar modeling. So he does solar forecasting. He looks at issues like geographic dispersion and how you predict how much solar power is going to be produced in a particular area at any time, and that sort of stuff. And his argument is that renewable energy is going to be so cheap in 10 years' time that all you do is build twice as much capacity as what you need. Okay. And if that is the case and you're producing too much power, then you just shut it down, because that is going to be cheaper than having storage. It's going to be cheaper than building big interties to neighbouring electricity systems, et cetera, et cetera. Now, I think that the downside of that argument is that as human beings, we don't like to waste things like large amounts of power. But on the other hand, if that was coupled with electrolysis to produce hydrogen, that might work rather well. I think the real problem with those ideas, and this is something that I haven't talked a lot about in the class, is that wind and solar energy are diffuse. In terms of square meters, to generate on average a megawatt of solar power, you need a huge area. And so if you're going to produce, say, all the electricity that Europe needs with solar energy, then I suspect the Sahara Desert is going to be covered with photovoltaic modules. So I think there are sort of a whole lot of issues that are going to occur for different countries in different ways. Okay, in Canada, for example, and Russia, we have very good offshore wind resources. So if as countries, if we're very sensible and wait for the rest of the world to develop offshore wind energy to the point where it's cheap, and we come in and buy it at that stage, then we probably have all the electricity that we need. So it's a fascinating question, and I think it'll depend a lot on where you are. I mean, I suspect it's the same for Russia, but one of the big issues in countries like Canada and Australia is actually distributing the energy that's produced. Big countries that, at least for some of the area, have low population densities, it's very expensive to extend the power grid to those remote communities. And so, issues like remote power can be very important as well. Okay. Now that we've finished our 6 weeks, would anybody like to comment on what you've learned and whether you think whether you got out of the course what you were anticipating, or are there things that you would like to know about that I haven't talked about, or any sort of feedback I would be very happy to receive?
Yeah, I could start that. I'm very appreciative for this course from you. And it was very interesting for us. We don't have any information about renewable energy. In Russia, we don't see a wind turbine every day.
No.
So, yeah, it's not very common for us. I mean, but it's very interesting that it's you have a high level of this development of this area. And for my first expression that it's always depends on the situation when we are in what point we locate it. So thank you very much. I think it's very interesting for us.
Thank you. And I hope I've also convinced you that there's no one solution to the world's energy problems. I think wind energy is going to play a role. I think photovoltaics will play a role. Storage will play a role. Hopefully fusion sometime in the not too distant future will play a role. And hydrogen, I think, is bound to play a huge role. So, it's going to, our energy systems of the future are going to be much more diverse and distributed than they are now. And I think there's a lot of high-level research and development and technological advice and decision-making required for all that. So, yeah, okay.
Also, one thing what I want to add, that we always wrote in our motivation part of the articles that we working with extending of operating conditions of Francis turbine, because in the future we will try to cover different power consumption and different power producing, and we need to extend the range of operating conditions of the Francis turbine. And it's just a words, and right now we just know something new about this. Why we should do this?
Yes, that's very true. Yes, I think it's that indicates that a lot of the technologies that will be used in the future are going to be used in conditions that they weren't necessarily designed for in the first place. Yeah. Okay. Anybody else have any comments or reactions they would like to pass on? Okay, well, hopefully you've got some useful information out of it, and I would be very happy for any feedback you would like to give. Either, feel you could talk to Ivan or Rustam, and they can pass on comments as well. I would be happy to get them that way, and I'm hopeful that I'll be able to see at least some of you in Novosibirsk in June next year, if the COVID variants will allow us. I will be there in June. So hopefully that's the case. Yeah. Anyway, we probably won't know till May.
Who knows?
Yeah. Okay then. Well, thank you very much for attending and listening. I've enjoyed it. It's been a challenge to sit in a room in Canada and talk to people halfway around the world. And as I said, I look forward to meeting at least some of you next year. So, and Ivan, you'll let me know when Daniel's done the calculations, and we can set up a Zoom meeting. Okay, then. Anything else before we finish? Okay.
Thanks. So, Merry Christmas.
Merry Christmas.
Wishes. Yeah.
What do you say?
Merry Christmas.
You do say Merry Christmas?
We don't. I know that you say that.
I know. Okay. Can I make you laugh by trying to say some Russian?
Sure.
Okay. So what is your? Do you say Happy New Year or something like that?
Yes.
So what's that in Russian?
С Новым годом. С Новым годом.
Новым годом.
Yeah.
Everybody can have a good laugh now.
Yeah.
Yes, I'm very glad that I didn't have to give these lectures in Russian. So thank you very much for listening to me in English.
Thank you.
Okay. Goodbye.
Thank you. Goodbye.
Bye.